Welcome to Chemistry with Miss E. Today we're going to find the connection between Bohr models, ion charges, and why these elements have the ion charges that they do. Your teacher might make you memorize the charges, but if you can understand why these elements have that charge, you will be so much better off, especially when it comes to periodic trends and understanding why elements act the way that they act, okay? So first I want to start with just the ion charge trend in general, okay? So whenever you have elements existing as ions, this is the pattern that it takes on the periodic table. You have your group 1 with a +1, group 2 with a +2. The transition metals change, right? They vary, it just depends. I call the transition metals the fake people of the periodic table. They act different depending on who they're with. So for example, titanium in one compound could be +2 and then it could be +3. So it changes, okay? There's not a set pattern to that. You have this column here, group 13, which is +3. You have group 14, which they are plus or minus 4. The minus sign here is because of carbon. Carbon has a -4, but everything else down is going to take that +4. You have -3, -2, -1, and 0, okay? So looking at this, you're like, oh, the noble gases, right? Noble gases are the last column, the last group on the periodic table. They have no ion charge, and there's a reason for that, okay? They're very noble, right? There's a reason that they have that 0 ion charge. So let's look at two examples here, and I'm going to really make sure you understand why these elements have the ion charge that they do. So we're going to take sodium, for example. I pulled it out of group 1, and I started to make the template for the Bohr model here, okay? So this is sodium. Sodium on the periodic table, right? It is element 11, and it has a 22.99 mass, right? So what that means is it has 11 protons, 11 electrons, right? And it has a 23 mass number, so 23 minus 11, right? That's going to tell me my number of neutrons, and so that's going to give me 12 neutrons, okay? Let's place those inside this Bohr model accordingly. So we have 11 protons here. We have 12 neutrons here. Protons and neutrons belong in the nucleus, very heavy, very dense, the central area right here of an atom. And then the electrons we need to place accordingly, okay? So 2 electrons fit on the first ring, so we have 1 and 2, right? And then 8 can fit on the next one, so 1, 2, 3, 4, 5, 6, 7, 8, right? Electrons do not like each other, right? They're negative particles. Negative does not attract negative, so they're going to space out, okay, across these Bohr model diagrams. And then I have, now that's 8 plus 2, so we're at 10 electrons total. Sodium has 11, so I need to place one more on this outside ring, right? It's very lonely out there, okay? There is one singular electron sitting on the outside, on the last orbital shell of this atomic model, of this Bohr model diagram for sodium. And here's something that's very important, okay? And it's gonna, once I tell you this, if you haven't learned this already in chemistry, this is a huge founding principle for a bunch of chapters to come in chemistry. And it's something called the octet, okay? Octet. For several reasons, right? For stability and just how it is, elements desire 8 right? 8 valence electrons, okay? Valence electrons. So valence, it could be valence, it's kind of tomato, but valence electrons are the electrons that are on the outermost ring, okay? So these are your valence electrons here, okay? There's only one, okay? It's the only one on the outermost ring. The ones inside are called core electrons, okay? This is your valence electron. 8 valence electrons is what the elements want. And so if you notice, sodium has 1 valence electron. It is 7 away from having an octet, okay? So it could gain 7 electrons somehow, some way, or, right, it could just get rid, right, of this last outer electron. Okay, so if it gets rid of the last outer electron, then this entire ring on the outside, right, almost kind of disappears per se. And so what do you have underneath? Oh my goodness, you have an 8 electron count around that outer energy level, right? And so by sodium getting rid of that 1 electron, so aka it's losing a valence electron, meaning it's going to get a +1 charge because it lost an electron. An electron's negative, so if you lose negativity, you will be positive, right? And so this is a +1 charge. So all of the elements in the group 1 column on the periodic table do that same idea, okay? And why do they have a +1 charge? Because they need to get rid of that outer valence electron, because underneath they have an octet. It is way easier for metals Okay, metals, which are from this side all the way below this staircase, the metalloid staircase ladder, so much easier for metals to get rid of their valence electrons because underneath they have that octet, okay? Let's look at an example for your nonmetal. So we have fluorine here, for example. So fluorine, right, on the periodic table, let's get the data here. If I were to look at it square and zoom in, right, we've got 9 and a mass of 19, right? And so that means it has 9 protons, right? So 9 protons, right? We've got 10 neutrons, 19 minus 9. And then we have 9 electrons. So let's draw those. We've got 1, 2 on the first one, and then 3, 4, 5, 6, 7, 8, 9. Right? So a total of 9 electrons here. If you look at the outer ring, right, looking at those valence electrons, this octet that all of the elements, right, for the most part are striving for, you've got 2, and then 3, 4, 5, 6, 7, 8, 9, right? On the outer ring, though, you have 1, 2, 3, 4, 5, 6, 7. Oh my goodness. So fluorine is how many away from an octet? 8 valence electrons. It is 1 valence electron away from an octet. And so you bet it's going to do anything it can, right, to get that last electron. And so it does. It's actually going to take one in, right? It is going to pull in an electron via bonding, right, which we'll get to, with another element. And so it's going to get that electron, right? And so there you go. Now after pulling in that electron, so taking in a negative particle, it's going to have that -1 charge, just like all the other nonmetals here in this column, right? Group 17, the halogens, right, as we know them. And so you can actually see this is a love story in disguise, right? Sodium has 1 valence electron that it wants to get rid of. Fluorine wants 1 valence electron. And so you actually notice when you put sodium and you put fluorine together, right? You have sodium with a +1, fluorine with a -1. They actually end up making a perfect match, right? Sodium fluoride. And that just gets into the start of all of the bonding unit and the amazing things that form when elements decide to bond together, right? So there you go. So Bohr models and ion charges, right? Just to recap, metals will always take a positive charge. They're going to be your cations, right? So positive ions taking a positive charge because they lose electrons. They want to give up those electrons in that outer ring, right? If it were a +2 charge, then they'd get rid of 2 electrons on their outer ring, right? Because again, underneath, they've got that full stable octet shell. Nonmetals, on the other hand, are going to pull in electrons, right, to itself. Those are your anions, and they're going to gain electrons, right? Anions, and they're going to gain electrons to achieve that octet. So again, noble gases, right? They have a zero ion charge. Why do they have a 0 ion charge, right? Because they have 8 valence electrons, right? If I were to draw, let's do, neon, for example, right? It would literally have, right, 8 valence electrons surrounding itself. Does it need electrons? No, it's got the 8, right? It was born with the 8 electrons that it needs, that all the elements want, and so that's why they're so noble, right? The kings and queens, the noble gases, because they were just born prepared, right, with the outer octet shell. So there you go. That's why they have an ion charge of 0, right? There are obviously some exceptions to this trend, and if you're in honors chemistry or college chemistry, your professor should count those, should give you those exceptions. For example, the transition metals or elements that don't achieve an octet, such as hydrogen. Hydrogen is happy with 2, right? It's happy with a ditet, should I say, right? So just 2 valence electrons because it's a very small atom. But there you go. That is why the elements have the ion charges that they do when it comes to octets and understanding at the atomic level, right, their Bohr models. See you on the next one.